Hello everyone. So far, we've seen two tests for determining the convergence or divergence of a series, the divergence test and the integral test. Last time, we studied the integral test, and in many ways, it was a more powerful tool than the divergence test because it enabled us to determine both convergence and divergence. The idea was instead of asking whether a series converges, we would turn the series into an analogous improper integral and ask whether that integral converges or not. The upshot was that evaluating an improper integral is generally easier than finding the sum of a series. But this is also a serious disadvantage of the integral test, because although evaluating an integral is easier than finding the sum of a series, it's not that much easier, and there are certainly many, many integrals that we are completely unable to evaluate, or would be a nightmare to try. But if you remember from when we were talking about improper integrals, we had a trick to get around this, provided we're only interested in determining convergence versus divergence of an improper integral, and we don't care about the precise value of the integral. That trick was the integral comparison test, and there is an analogous test for series. It's called the comparison test, or the direct comparison test. As a reminder, the basic idea behind the integral comparison test was we compare a complicated improper integral to a simpler one whose convergence status we knew in advance. If the simpler integral was convergent and bigger than the complicated integral, we could then conclude the complicated integral was also convergent. And conversely, if the simpler integral was divergent and also smaller than the complicated integral, we could conclude the complicated integral was also divergent. The basic principle at work was, if you are smaller than something finite, you are finite, and if you are bigger than something infinite, you are infinite. But of course, that basic principle is certainly not special to integrals, and we can apply the exact same reasoning to series. Let's say we want to determine the convergence status of some complicated series whose terms, a sub n, are all positive. And let's say we also have a relatively simple series with terms b sub n that are also positive, but whose convergence status we know in advance. If the simple B series is convergent and each term B sub n is bigger than the corresponding term A sub n in the complicated A series, then we must conclude the sum of the A series is smaller than the sum of the B series, which is finite in this case. Thus, the A series converges. And conversely, if the simple B series is divergent and each of its terms B sub n is smaller than the respective A sub n term in the A series, then the sum of the A series must be bigger than the sum of the B series, which is infinite in this case. Hence, the A series must also have an infinite sum, or in other words, be divergent. So that's the direct comparison test. Now, before jumping into the examples, I need to tell you about one other little fact that is useful throughout the section. Recall that the integral from 1 to infinity of 1 over x to the p dx converges if and only if p is strictly greater than 1, and diverges if p is less than or equal to 1. Well, by the integral test, an analogous fact for series also holds. The series sigma sum from n equals 1 to infinity of 1 over n to the power p converges if and only if p is strictly greater than 1, and diverges otherwise. We'll be making use of this fact quite often in the examples. All right, let's try out some examples then. So we're going to try to decide whether the following series converge or diverge, and the first one we'll start with is this one. So sigma sum from n equals 1 to infinity of n squared divided by the square root of n to the 9th plus n cubed plus 10. All right, so the goal with these things, so using the direct comparison test, in practice, it's very similar to the integral comparison test. The way we want to handle this sort of thing is we want to go and find a way to either make the terms here, so the n squared over square root of garbage, make that either bigger or smaller, but importantly, we want to make it simpler. So we want to somehow modify the terms of the series in order to make them simpler and change their size, either to make them bigger or smaller, and hopefully in a way that lets us apply the direct comparison test. But for now, let's just focus on making this thing simpler. All right, so certainly it looks like there's room to do that. We have, especially the denominator here is quite complicated. We have square root of n to the 9th plus n cubed plus 10. Well, one thing I can see right away is one way to kind of make this thing simpler would be if the n cubed and the plus 10 were gone. So if those weren't there, this would be a lot simpler. And even more than that, that would also be suggestive of the long-term behavior of these terms. As n gets really, really big, then the n cubed and the 10 are going to matter less and less. They will be outcompeted by the n to the 9th term. So as far as that goes, I think a good thing to try to compare this to would be n squared over the square root of n to the 9th, which simplifies into n squared over square root of n to the 9th. That means I cut the exponent in half, so that becomes, I think, n to the 4.5, which will simplify into 1 over n to the 2.5. All right, so the question is then, okay, so this is so I've made this thing simpler, certainly, but have I made the terms bigger or smaller or neither? Have I just kind of mixed them up and I'm not really sure what I've done? Well, let's see what I've done. So what I've done is I've gotten rid of the n cubed and the 10. That's what led us to that. And in doing so, what that will wind up doing to the denominator is it will shrink the denominator because I'll be adding together less stuff. And so if I shrink the denominator, then that's going to inflate the size of the entire fraction. So as far as the terms go, if I just copy the terms down over here just to make it clear what I'm saying, in hopping from this step to this step, I have made the terms bigger and hence the series bigger. So in this case, what I can conclude is this series has to be smaller than or equal to sigma sum from n equals 1 to infinity of 1 over n to the 2.5 power. And this you should recognize as being a p-series, where p, in this case, is 2.5, which is definitely strictly greater than 1. And so this is going to be a convergent series. And so what have we done? We've shown that the series we're interested in is smaller than a convergent series. So therefore, this one has to also be convergent. Maybe I'll snake it through here if that's okay with you guys. All right, so that's one example down. Let's look at another one. So how about this one? So we'll have sigma sum from n equals 3 to infinity of 6n plus 1 divided by n squared minus n minus 3. All right, so this is once again a rational function, or at least the terms are. So a good strategy then to go and make this thing look simpler, or a good series to compare this to, is the series where we just focus on the leading terms, because after all, that's going to be the long-term behavior of the terms of the series. If n is really big, then these lower order terms, the minus n minus 3 and the plus 1, are just not going to really matter. So this thing we will approximate by the sigma sum from n equals 3 to infinity of just, let's say, 6n divided by n squared, which in our case would be, I think, just 6 divided by n. All right, so that's one way to make this thing simpler, although now we need to see, in doing this, did we go and make the function bigger or smaller or neither? So that's the other ingredient we need to use the direct comparison test. So what did we do in order to obtain this? Well, I got rid of the plus 1 from the numerator, so I shrank the numerator. And what did I do? I got rid of these subtractions. I'm not subtracting n, and I'm not subtracting 3. So if I'm not subtracting stuff, then that's making the denominator bigger. I'm no longer subtracting, therefore n squared is bigger. So I've made the numerator smaller and the denominator bigger, so that will have the overall effect of not just of shrinking the overall series. All right, so we have this relation right here. And so what about this? Do we know whether this thing converges or not? I think yes, we do. I can make it a bit more explicit if I factor out the 6. So if I factor out the 6, you can see that we're left with 6 times the harmonic series, or a p-series where p is equal to 1. And that is a divergent series. So our original series is greater than or equal to something infinite, therefore this thing must also be infinite. It must diverge. All right, so I think we're getting the hang of that. So let's do another one. How about this one? So sigma sum n equals 5 to infinity of n cubed minus 2 divided by 8n to the fourth plus 6n. All right, so usual trick. Let's go and approximate this series by the version where we get rid of the lower order terms. So we just have n cubed and 8n to the fourth. That's what the series will be approximately equal to in the long term. In other words, for big values of n. So if I do that, I'm going to have sigma sum n equals 5 to infinity of n cubed divided by 8n to the fourth, which I think will simplify down into 1 over 8n. All right, so now we'll ask the question, what did this make the series bigger or smaller or neither in doing this approximation? Well, let's see. So I got rid of a subtraction in the numerator, so that will make the numerator bigger. And I got rid of an addition from the denominator, which will make the denominator smaller. So numerator increased, denominator decreased. That is going to have the effect of making the series larger. All right, so we have over here sigma sum of 1 over 8n. So does that converge or diverge? Well, if I factor out the 8, or the 1/8, as it actually is, this will be 1/8 times the sigma sum from n equals 5 to infinity of 1 over n. And that, as we saw before, that is the harmonic series. Doesn't matter if you multiply by an eighth, and 1/8 of infinity is still infinity. So this is infinite. So we've shown that the original series is less than or equal to, less than or equal to infinity. Well, that's kind of embarrassing because everything is less than or equal to infinity. So, shoot, so we haven't actually shown anything, have we? We don't know if this thing converges or diverges because things that converge are less than or equal to infinity, and things that diverge are also less than or equal to infinity. So this is not going to work. So, okay, so apparently this series was the wrong series then to compare our original series to. So this one was maybe the most obvious approximation to do, but it's one that doesn't actually yield us any useful information. So we're going to need to try to find some different way to modify the series in order to get an inequality that we prefer. Or, well, maybe not that. So we still don't know whether this thing converges or diverges, but we need to get a comparison other than this one. All right, well, in order to help us kind of aim a little bit, let's try to think about whether this thing converges or diverges just from kind of some intuitive analysis. So like I said, so going back to what we originally had, I said that this thing is approximately equal to this series, and so that doesn't necessarily mean that the convergent status of these two series have to be the same, but it is suggestive of it. So this series is approximately equal to the harmonic series for large values of n. So in that case, it would be reasonable to guess, even though the direct comparison test doesn't confirm it for us, it would be reasonable in this case to guess that this series diverges. And so if that's the case, what we want to do then is we want to modify this series so that we get a smaller series. We want something smaller that we know diverges. So I'd like for you guys at this point to go and try to think about what modifications could you make to this to make it both smaller and give you a series that you know definitely is divergent. So go ahead and pause it and see what you come up with. All right, so I don't know if you came up with the same thing that I did. I expect this problem has many different ways that you could solve it, but for what it's worth, here was what I was thinking when I first saw this. All right, so if we're trying to shrink this series, and the terms is a fraction, there's two ways we can do that. We can make the denominator bigger, or we can make the numerator smaller. So in this case, well, let's see. So there's that. The other thing, though, that I want to go and make this thing simpler, because I need a simpler looking series if I want to hope to know its convergence status, which is the whole point of the direct comparison test. You compare it to something whose convergence status you know in advance. So what I would like to do, which was kind of the inspiration that I did over here, was I wanted to get rid of these annoying lower order terms so that I could go and simplify this down into a nice looking P series. So I still want to follow that that strategy for now. So except what I need to do, so what I want to do, let me back up a second. Let me focus on the denominator. I would like to turn the denominator into something where it is purely a single term with no lower order terms. The simplest way to do that is what I did over here. I just get rid of 6n, but of course that throws the denominator into the wrong direction. It makes the denominator smaller. I need the denominator to grow. So here was my thought then for how you can get the terms to be the same order without just dropping the 6n, which we're not allowed to do. So I just copied the numerator for right now. So here's my thought. So the issue is 6n is a lower order term. I wish it wasn't there, but the next best thing is, well, okay, so it's not a, so it's a lower order term, but if it was the same order as 8n to the fourth, then I could combine them and, in a sense, make it go away. And I think I can do that because if I go and swap out the n for n to the fourth, if I just make n go to the fourth power here, taking a number that is greater than or equal to 5 and raising it to the fourth power is definitely going to make the number bigger. And so I've made the denominator larger overall and hence shrunk the entire fraction. So if I do that, then I wind up with this right here. So I have sigma sum of n cubed minus 2 over, I guess, 14n to the fourth. Now I could try to play the same game with the numerator over here. I could go and turn, say, this 2 into, say, a minus 2n cubed, but that's actually not something I can do in this case if I'm trying to use the direct comparison test, because then I'll have n cubed minus 2n cubed, which will be a negative n cubed, and the direct comparison test only works if we have a series with positive terms, but now the terms are negative. We have a negative n cubed, so I can't actually cheat it out that way. But the good news is, I don't think I really have to go and get rid of the minus 2 from the numerator. It would be nice, but I don't think I have to, because having a sum or difference in the numerator is not so bad, because I can just go and split the series apart, or really the fraction apart, at the additions and subtractions in the numerator. So what I'm going to do is break this thing apart into sigma sum n equals 5 to infinity of n cubed over 14n to the fourth minus 2 over 14n to the fourth. And if I quote-unquote distribute the series, the sigma sum, I'm going to have sigma sum of this thing, which I think simplifies into 1 over 14n, minus sigma sum of, I guess that's just going to be 1 over 7n to the fourth. All right, so let's see what we've got. So I have two series now, which I'm subtracting. This first one is a scaled version of the harmonic series. In other words, it's going to be a scaled version of infinity, so it's also going to be infinity. This is a divergent series, and I'm subtracting a series where we have basically 1/7 times the series, the sum of 1 over n to the fourth. And p in this case is 4, which is greater than 1, so this thing is convergent, it's finite. So I'm taking infinity and subtracting something finite, so I am going to wind up having infinity as a result, and I think that's exactly what I wanted. So I have the original series is greater than or equal to something infinite. Therefore, this thing must also be infinite.
Okay, so far we've just been looking at sigma sums where we've basically had a rational function or something close to that. We've had polynomial over polynomial or something similar to that. So let's mix it up a little bit. Let's try this series. Say we have sigma sum n equals 2 to infinity of 1 over 7 to the power n plus n. All right, so I think there's at least two obvious ways to go and make the terms of this series simpler, which come readily to mind anyway. They're not necessarily the only options, but they're the ones that seem most obvious. I could go and drop the plus n and just have 1 over 7 to the n. Or I could drop the 7 to the n and just have 1 over n. And in either case, I would be removing something positive from the denominator, which would have the effect of shrinking the denominator and hence inflating the fraction. So in that case, we have to decide which one do we want to remove. Well, I don't know, eeny, meeny, miny, mo. Let me start off with removing the 7 to the n. So if I do that, then I'm going to get the series sigma sum of 1 over n, which is one whose convergence status I know very immediately. This thing diverges, it's infinite, and so this thing is less than or equal to infinity, which tells us absolutely nothing. All right, so we wound up in the same boat that we were last time. Oh well, that happens. Okay, so maybe throwing away the 7 to the n was the wrong choice. So let me try the other way around. Let me throw away the plus n in this case. So in that case, my bigger series will be 1 over 7 to the n. And this is a geometric series, actually. If it's not completely clear yet, let's go and make it a little more clear. So I have a 1 on top, but 1 can be written as 1 to the n. And then I can factor out the n in order to get sigma sum of 1/7 to the power n. And this must be finite, it must converge as a geometric series because 1/7 in absolute value, or without, is strictly less than 1. All right, so in this case, we've shown that the original series is less than or equal to something that's finite, it converges, and so thus the original series has to do likewise and also converge. If you're smaller than something finite, you are also finite. All right, so I have a couple more for you guys. So take a look at this one. This is one that I might call a fun one. You know what that means. Sigma sum n equals 1 to infinity of sine squared of n plus the arctangent of n plus e to the minus n, all divided by n to the 9th power plus n to the 1/3 power. All right, so this one certainly looks a bit overwhelming. We have three very different kinds of function on the top. We have a trig function squared, and then we have an inverse trig function, which is a related but nevertheless very different animal than a trig function. And then we have an exponential, which seems to have nothing to do with any of that, and the denominator is a polynomial, except it's not really because there's a cube root down there. So this is just a completely messed up function. So, but again, don't try to take it all in one go. One thing that I note immediately about this, again, is all of these functions that are on top, they all have this property in common. They are all bounded functions. That is to say, they all have an upper bound and a lower bound, or at least they do if you are within the interval from 1 to infinity. Why is that? Well, so let's look at each of the three in turn. So sine squared is going to be bounded from below by 0 because it's a square. If you square something, then you can't go below 0. But its upper bound has to be 1 because the range of the sine function is -1 to 1. If you square it, well, if you square -1 or 1, it's just going to go to 1. So sine squared certainly can't be any bigger than 1. Arctan, just by its nature, remember what this thing is doing intuitively. The arctangent function goes and converts slopes back into angles. So if I go and have an infinitely large slope, then the angle that corresponds to is 90 degrees, or in other words, pi over 2 radians. So this thing has a maximum at pi over 2, and its minimum is going to be, well, I guess it's an increasing function. If I increase the slope, then the angle that I get out is going to increase. So its lower bound has to be the result of just throwing in 1 into this. It's an increasing function, so its lower bound corresponds to the lowest input that we can plug in. And e to the minus n, in this case, is also bounded. As n gets really, really large, in the limit, e to the minus n goes to 0. It never actually touches 0, but it goes toward it, and that forms the lower bound forms a lower bound for an exponential function. An exponential function can never be negative. It can never be equal to 0 either. So a lower bound for this is definitely 0. But this is also a decreasing function, and so that means it has an upper bound which occurs at the lowest value of its input, in this case n equals 1. So it has an upper bound at e to the -1. Anyway, so the point of all that is just to go and show that, yes, all of these are bounded, and so what that means is, with an inequality, we can either, if we want to go and shrink the numerator, we can go and replace each of these 3 functions with their respective lower bounds, and if we want to increase the numerator, make it bigger, then we can replace each of these 3 bounded functions with their upper bounds, which will be a great simplification in this case. But I guess we have to decide which one we want to do. I guess we could just try one and see what happens. That's certainly a fair strategy. But let's see if we can anticipate it in advance a little bit. So if I was to pretend that all of these functions on top were just gone and replaced with, say, 1 over something, this would be 1 over n to the 9th plus, well, something that can be ignored for large n values. So we have 1 over n to the 9th, and if I was adding up that would be a convergent series by the p-series test, right? So 9 is bigger than 1. This would be convergent if we can ignore everything except the n to the 9th, basically. So in that case, I'm going to guess right now that this series converges. And if so, to use the direct comparison test, I need to go and compare this series to a bigger series which is also convergent. So I need to inflate these terms. All right, so to inflate the terms, how can I do that? We'll focus on numerator and denominator one at a time. So if I want to go and make the series bigger, then I need to make the numerator bigger. And because these are all bounded functions, there's an easy way to do that. I will just replace each of these 3 functions with their respective upper bounds. So sine squared has an upper bound at 1. Arctan's upper bound is pi over 2. And e to the minus n has an upper bound at its initial value of n, because it's a decreasing function. So this will have an upper bound of e to the -1, whatever that is. All right, so that's numerator. What about denominator? So if I want to make things bigger, I need to shrink the denominator. And here I think there's a very nice way to do it. I can do exactly what I want. I can just get rid of the plus n to the 1/3 power. That will have the effect of shrinking the denominator. All right, so I think we've got what we want. So the numerator looks rather complicated, but remember, it's just a constant. It's going to be just some sort of number. If you throw it into your calculator, it'll approximate it for you. But it's just some sort of constant, so you can factor it out if you want. So this thing becomes whatever that constant is. Doesn't matter what it is. Constant times sigma sum of 1 over n to the 9th. And as I already mentioned earlier, that is convergent. Or in other words, the sum is going to be finite, whatever it is. All right, so mission accomplished, I think. The original series is less than or equal to something finite. Therefore, this series must also have a finite sum. In other words, be convergent. All right, and with that, I have one more example for you in a similar vein. It's another fun one. Although it's less fun now because I think you know the trick. You can see how sadistic I am. All right, so we have sigma sum of cosine of n plus 4 plus e to the minus n, all divided in this case by the square root of n. All right, so once again, there's no need to panic just yet at the numerator. I mean, it looks horrible and ugly, but once again, we're in the same boat that we were in before. All of these functions are bounded. So cosine is bounded between minus 1 and 1, and e to the minus n, if we're restricting ourselves to the interval from 1 to infinity, is bounded between 0 as a lower bound and e to the minus 1 as an upper bound. So yep, numerator is all bounded. And so in that case, that gives us a very quick and easy way to go and either shrink the numerator to something simple or inflate it to something simple, depending on what our needs are. And on bottom, what we've basically got is n to the power 1/2. All right, so in order to simplify this, we can turn, basically, the fact that that the numerator is bounded means that we can convert the numerator into a constant, but we need to decide in which direction do we want to do that. So again, let's go and pretend for the moment that the numerator was gone, or replaced with just a 1. Then we would have 1 divided by the square root of n, or in other words, we would have sigma sum of 1 over n to the power 1/2. And this would be a divergent series, right? By the p-series test, because 1/2 is less than or equal to 1. So in that case, that makes me think that this series probably diverges. And to verify that, using the direct comparison test, I need to go and shrink this series into something smaller, which is also divergent. So my goal is to shrink this function, or shrink the series. So in that case, what I'll want to do with the numerator is I'll want to shrink the numerator. And a good way to do that, since all the functions are bounded, is to replace each function with its respective lower bound. All right, so cosine's lower bound is -1. You can't get any smaller than that, or any lower than that. 4 can just stay by itself. That's fine. And e to the minus n, that has a lower bound at 0, like all exponential functions do. All right, and if I clean that up a little bit, that gives me 3 divided by n to the 1/2. So I have 3 times something that we already established is infinite, so this thing is also infinite. So yep, yes indeed, this series is greater than or equal to something infinite, so it must also be infinite. The series definitely diverges.
All right, the direct comparison test is pretty great, but it definitely has some limitations, as you might already foresee. Perhaps its biggest weakness is it requires the two series we are comparing to have an inequality relation between them. That is, we need one of the series to be bigger than the other series. But worse still, we need to make sure the correct series is the bigger one. If we compare a series to a bigger series that is divergent, we learn nothing because we would have essentially shown that our series is less than or equal to infinity. But everything is less than or equal to infinity, so we get no useful information. So we would like to have a test that isn't so picky about how the two series we want to compare relate to one another. Well, spoilers, it turns out there is such a test. It's called the limit comparison test, and it allows us to compare the convergence status of two series without worrying about the relative sizes of the respective terms of either series. The main requirement is that both series need to look sufficiently similar, in a sense I'll define in just a second. The idea, once again, is we take two series with positive terms, one of which we should think of as being complicated and the other simple. We then consider the ratio between the respective terms of the series, so the ratio a sub n over b sub n. We then take the limit of this ratio as n goes to infinity and see what we get. As long as we get something, anything, that is greater than 0 but less than infinity, that is something strictly positive but finite, the limit comparison test tells us that the two original series have to share the same convergence status. Either both converge or both diverge. So why does this work? The explanation is actually not that complicated and something I think within your grasp, but it is a little bit involved, and I don't want to spend too much time in this video bogged down in those details. So here, I'll just give a high-level explanation. Let's say the limit of a sub n over b sub n is equal to k, where k is some positive finite number. Think about what this means. It means that if n is very large, then the ratio a sub n over b sub n closely approximates k. And the bigger n is, the better the approximation. Rearranging this slightly, it also means a sub n is approximately equal to k times b sub n, which in turn means the sigma sum of a sub n approximately equals the sigma sum of k times b sub n. Or at least it does if we restrict ourselves to big values of n, whatever that means. Now let's factor out the k from the sigma sum on the right-hand side. Given this equation, what happens if the sum of the b series is infinite? Well, then the right-hand side becomes k times infinity, and since k is strictly positive, meaning it is not equal to 0, k times infinity must also be infinity. Hence, the sum of the a series is also infinite. That is, both the b series and the a series are divergent. On the other hand, if the sum of the b series is finite, then the right-hand side becomes k times something finite. And since k is also finite, the product must be finite, and hence the sum of the a series is also finite. So both the b series and the a series are convergent. Of course, this argument only works as long as we are only considering big values of n, whatever that means. But the conclusion doesn't change if we add back in the small values of n, because there can only be a finite number of terms corresponding to these small values of n. And if you add a finite number of terms to something, you can't make it switch from being finite to infinite, or vice versa.
Alright, so time to try this out on some examples. So once again, the task is to decide whether these series converge or diverge, and the first one we'll look at is this one. So sigma sum n equals 5 to infinity of n cubed minus 2 divided by 8n to the fourth plus 6n. All right, so you can see again that we have the terms are given by a rational function. So it turns out when you're using the limit comparison test, if you have a rational function, a very good choice for what to compare the terms of the series with is the version of this rational function where you've gotten rid of the lower ordered terms and you've also gotten rid of any leading coefficients. So in this case, let's say that this is my a sub n, this is my complicated a sub n. I'm going to compare it against n cubed divided by n to the fourth. So I strip away everything except for the highest powers of n. And so that will be my b sub n, which of course can be simplified into just 1 over n. All right, so according to the limit comparison test, what I'm supposed to do is, well, let's consider the ratio of a sub n over b sub n. So what I need to do is I need to take this formula and divide it by 1 over n. But if I'm dividing by 1 over something, that's the same as multiplying. So really, what I've got going on is I have a sub n over here, and I'm going to multiply by the reciprocal of b sub n. So 1 over b sub 1 over b sub n is just going to be n, so I'm multiplying this thing by n. So if I do that, it'll distribute itself to the two terms in the numerator, and I'm going to get n to the fourth minus 2n divided by 8n to the fourth plus 6n, same thing downstairs. So in this case, if I go and take the limit now as n goes to infinity, what happens? Well, so here's where our choice of b sub n comes in handy. By multiplying this, by multiplying a sub n by n, we have now made the numerator and denominator have the same order. It's now a quote-unquote equi-heavy rational function, which means in the limit, it is going to converge to the ratio of the leading coefficients. And in this case, the leading coefficients are 1 and 8. So in that case, this ratio, a sub n over b sub n, is going to converge to 1/8. And 1/8 is definitely a strictly positive number, and it's certainly a finite number, so we are in good shape. So in that case, we know then that the convergent status of this series is going to be the same as the convergent status for sigma sum of b sub n, which in this case would be sigma sum of 1 over n. And that is the harmonic series, or basically the harmonic series, which we know is divergent. And so the limit comparison test assures us that, okay, if this guy diverges, then so does that one. So this diverges. All right, so let's do another one then. So let's try this one out. So sigma sum, n equals 1 to infinity, of the square root of n plus 3 divided by n squared plus n minus 1. All right, so this is not strictly speaking a rational function because we have a square root on top, but it's the same basic principle. If I go and write the square root as a power, that's going to be n to the 1/2 plus 3 divided by n squared plus n minus 1. So same principle applies. What I'm going to do is I'm going to strip away all the lower order terms and only look at the higher order terms without their coefficients, although in this case they don't even have any coefficients, or their coefficients are 1. So in this case, my comparison is going to be to n to the 1/2 over n squared. And that's my b sub n, this is my a sub n. So this thing I think will simplify into 1 divided by n to the 1.5 power. All right, so let's take the ratio and see what happens. So what the limit comparison test tells us we need to do. So I take my a sub n, which is n to the 1/2 plus 3 divided by n squared plus n minus 1, and I need to divide by this thing, but this thing is a reciprocal already, so dividing by it is the same as multiplying by n to the 1.5. So times n to the 1.5 power. When I do that and distribute it through, I'm going to get 1/2 plus 1.5, that's going to give me n squared, plus 3n to the 1.5, divided by n squared plus n minus 1. All right, and just like before, because the order of the numerator and denominator are the same, the limit as n goes to infinity is just going to be the ratio of the coefficients, the leading coefficients. And so we're going to get 1 in this case, 1 divided by 1. And 1 is definitely strictly between 0 and infinity. So that's what this that's what I mean by this notation right here. You don't have to use this notation, but if you do, then you are certifiably cool, or at least according to mathematicians you are. Who may or may not have that much credibility. But anyway, if you care to use it, what this is saying is we're saying 1 is in the interval from 0 to infinity. Anyway, so the point is then, by the limit comparison test, this series and the series n equals 1 to infinity of 1 over n to the 1.5 have to share the same convergence status. And this one is a p-series where p is greater than 1. So this thing must be convergent. And thus also must that. Okay, so far we've just been looking at more or less rational or rational-esque terms for the series. So let's go and look at something a bit different. So how about this one? Sigma sum n equals 1 to infinity of 5 to the power n divided by 6 to the n minus 3. All right, so the idea behind the limit comparison test is we need to, well, compare the series to a series which is sufficiently similar in the sense that when you take the ratio and take the limit, you get something that is positive and finite. So we need something similar enough so that that happens. Looks to me like a good candidate in this case would be the version of the series where you just drop the minus 3, right? After all, if n is very big, then this minus 3 plays almost no role in the series, so that seems to me like a very good approximation. So let's compare the series, or the terms of the series, to this one, which is, if I factor out the n, is going to be 5/6 to the power n. Actually, now that I think about it, that's true, but I think I'm going to stick with this representation of it for now. All right, so let's take the ratio of a sub n divided by b sub n. So in that case, I'm going to have 5 to the n over 6 to the n minus 3, and then I have to divide by this thing, but dividing by something is the same as multiplying by the reciprocal. So I'm going to multiply by 6 to the n divided by 5 to the n. And let's see what we get. So the 5 to the n's are going to cancel, and I'm going to be left with 6 to the n over 6 to the n minus 3. All right, so now I need to take the limit as n goes to infinity. So in this case, it's a little bit tricky to do that, right? Because if I take them to infinity, both numerator and denominator are going to go to infinity. So the usual way we handle that is with L'Hopital's rule. But in this case, I think that would be a bit of overkill. I don't think we need to do that in this case, because I think a simpler way to handle this is if I could somehow split the fraction apart at the minus sign. Although I can't do that right now because it's in the denominator. I can only split a fraction across a subtraction sign or an addition sign if it's in the numerator. But why not put it in the numerator? The limit comparison test doesn't say that the complicated terms, whatever that means, have to be on top and the simple ones have to be on bottom. The limit comparison test is just as happy if you reverse the roles of a and b. So let me consider b sub n over a sub n, which would be just the reciprocal of this thing. So 6 to the n minus 3 over 6 to the n. And now break it apart and simplify. All right, and I think it's pretty clear what this thing is going to do in the limit. N goes to infinity, denominator goes to infinity, 3 divided by infinity is 0. So we get that this thing converges to 1, which is certainly in the interval from 0 to infinity. So yes, indeed, this series then, and this series have to be linked. And this is a geometric series, which in this case is going to converge, right? So 5/6 is less than 1 in magnitude. So this thing is going to converge. Since 5/6 is less than 1 in magnitude, and since these two are linked by the limit comparison test, this series also has to converge. All right, so far so good. So here's another example for you. I think this one's another fun one. So sigma sum, n equals 1 to infinity, of arctangent of n divided by the square root of n. All right, so the limit comparison test says that we need to, well, compare the terms a sub n to something that is similar enough to it. Although in this case, it's not really clear what sort of simplification we could really do to this, right? I mean, both the numerator and denominator look pretty much like atoms. How do you simplify arctangent of n all by itself to anything? How do you simplify just a naked square root of n to anything nicer? So it's not really clear here. So if you'd like, take a moment to go and pause and think about what sort of simplification or what kind of simpler looking terms you would choose that might work out. Maybe go and try a few examples and see what you come up with. All right. So again, what I came up with may not be the same thing that you came up with. There are probably multiple ways you could do this, but here's what I was thinking. All right, so yeah, it's true that none of these really admit a very clear algebraic way to go and simplify them any further, but one thing I do remember about arctan from all of the stuff we did with direct comparison was that arctangent is a bounded function. And so what does that mean? It means in the long term, if n is very large, which the series spends most of its life as being, then arctangent of n is going to be very, very, very close to pi over 2. It's going to be very close. In other words, it'll be very close to some constant upper bound. That's the main gist of it. So in that case, for the most part, let me just treat the numerator as just being a constant. So in that case, a good simple function to compare this with might just be, well, I could do pi over 2 divided by square root of n, but I think the limit comparison test is robust enough that I can just put any constant I want there. So I'll put the simplest one I can, just 1 over the square root of n. Let's compare it that way. All right, so that's my b sub n. So let's divide them and see what happens. So a sub n divided by b sub n. In this case, that is going to be arctan of n divided by root n. Divide by b sub n is the same as multiplying by just the denominator, so that's going to be just times the square root of n, which means they're going to cancel, which is very convenient. And so we're just going to get just plain old arctan of n. And as I already spoiled earlier, we know the limit of this thing as we take n to infinity. Limit of arctangent is just going to be pi over 2, and pi over 2 is certainly a positive finite number. So yes, indeed, the limit comparison test tells us that this series and the series where we have just 1 over the square root of n have to be linked in terms of their convergence status. And I think we know the convergence status of this thing. This is the same as sigma sum of 1 over n to the 1/2. And in this case, 1/2 is definitely less than or equal to 1. It is our p. So p is less than or equal to 1. That means this is divergent. And hence, so does that one. All right, so I have one last example for you guys, which, I mean, it's hard to believe, I think might be even funner than this last example. Yes, funner is a word. I will fight you. Sigma sum from n equals 1 to infinity of sine of 1 over n. All right, so if you feel so inclined, go ahead and pause the video and see if you can come up with a reasonable thing to compare this series with that will let you apply the limit comparison test. So I'll wait right here. All right. So if you couldn't find a good thing to compare it with, I don't blame you necessarily. It's a bit of it makes use of an approximation that we haven't talked about yet, but which is very common in physics and in other settings. So it turns out, for reasons that will be clear in a week or two, that the sine function of sine of something is very closely or very well approximated by just its input. So sine of 1 over n can be well approximated by just 1 over n, provided that the input is small. So if you're taking the sine of some, so in other words, if you're taking sine of theta is approximately equal to theta if theta is small. Whatever that means. And in this case, I think we can agree that 1 over n would be small, because as n gets very large, which the series spends most of its life as, then 1 over n is going to be a very tiny number. So this is actually a good choice for our approximation in this case, or at least I think so. Again, you might have found something else that worked. And if so, then that's certainly fine. But let's go and see what happens if I try this out. So that's my a sub n, and this is my b sub n. All right, so I take the ratio a sub n over b sub n. So in this case, I think I'm just going to wind up having sine of 1 over n times the reciprocal of this thing, which is just going to be times n. So that's a normal way to write it, but actually in this case, I'm going to break the mold a little bit. I think it's actually more advantageous in this case to write it as sine of 1 over n divided by 1 over n. The reason being, we can have 1 over n, 2 copies of it showing up in 2 different places, and that has some advantages. All right, so if I look at it as it is, what do I need to do? So I need to take the limit as n goes to infinity. So what's going to happen if I do that? Well, if I take n to infinity, then 1 over n is going to approach 0. And so that means my numerator and denominator are both going to approach 0 divided by 0, which is indeterminate, but means that we can use L'Hopital if we need to. So I could do that, although this looks like an awfully painful thing to try to L'Hopital, don't you agree? Taking the derivative of sine of 1 over n, that's going to be quite the ugly thing. And same thing with 1 over n. I mean, not so bad, but still something I'd like to avoid. So one thing I can do is note that, again, since 1 over n is appearing twice over here, and I already know what's happening as n goes to infinity. As n goes to infinity, 1 over n is going to 0. So let me just give a name to the 1 over n thing. I'm going to call that theta. And so the equivalent way to frame this problem is, instead of taking the limit as n goes to infinity of this thing, I'm going to take the limit as theta goes to 0 of this fraction, sine theta over theta. All right, so same thing happens. If I send theta to 0, then I get 0 divided by 0. So I need to use L'Hopitals. But L'Hopitals in this case is a lot easier to apply. Wouldn't you agree? So doing L'Hopital's rule, I take derivative of numerator and denominator. So numerator just becomes cosine of theta, and denominator just becomes 1. So this is just going to be cosine of theta. And what am I doing with theta? I'm taking it to 0 because n is going to infinity, n goes to infinity, then theta has to go to 0. So theta goes to 0, then I get the cosine, whoops, not an equal sign. Then I get the cosine of 0, which is 1. As theta goes to 0, as n goes to infinity. All right, and 1 is certainly a positive finite number. And so yes, indeed, the sigma sum of a sub n and the sigma sum of b sub n have to be linked. And of course, the sigma sum of 1 over n is famously divergent. All right, so that's the limit comparison test for you guys. Before we go, I want to go and make one other comment about the limit comparison test. So as I said earlier, it is a more powerful tool than the direct comparison test. But don't forget about the direct comparison test. Because although the limit comparison test is a more powerful test than the direct comparison test, there's still value in knowing and using the direct comparison test, just because it is a much simpler and quicker tool to use when it does work. And so an important skill to learn in math, as elsewhere, is how to tell what tool is best suited for a given problem. So you don't use a sledgehammer to swat a fly.